Hello, everyone. It will be a presentation about the future of wireless network. We will start from today technology, and we will move forward to future. And 50 years later, maybe we need a connection to the Mars. So what will be the solution? So it will be my presentation. Let's move ahead. First of all, we start from today's technology, and we have to understand where the data rates come from. That's the place that the most people think the data rates come from that bird. Some engineers send that bird, and data rates is pop up to your face. But if you want to open the technology for you, then you can understand the basis of the technology and where the data rates come from. It's a simple formula, but we have to understand the part of it. That's when the radio tells you the data rate is 54 megabits per second, these parts involved to that name, to that number. So let's open it up and see what are they. First of all, let's start with carrier. What is the carrier? If you want to ship something to other country, maybe you need a carrier, something like a container, 20 foot, 40 foot. If you use a bigger container, you can send more accessories, more goods. It's exactly the same here. If you use a bigger subcarrier, bigger carrier, you can transmit more data. What is the carrier? You choose that when you selecting a channel. You choose, for example, this channel, 5180. That you're going to choose a channel, but when you choose a channel, you choose the lower and higher frequency that you are using. Here we are using 20 megahertz channel, 20 megahertz channels. If we double the channel width, we will make double the throughput. When we have a closer look to that carrier, when we open it up and make a closer look with a spectrum analyzer, we will see it's not flat, it's bouncing here. What is that? Why it's not flat? Why it's bouncing? They are speaking with that bounces. In OFDM technology, it split the carrier into subcarriers, small carriers, just like small boxes inside a container. And each box contains our data. So the subcarriers can deliver our data and use the small channels. For example, in A and G standard, we are using 52 subcarriers. 4 of them is pilot carriers, it's just for syncing. And the rest of the subcarriers can carry us data. To improve the efficiency, to make it better, to make it higher speed, what the engineers did is giving you some more subcarriers to make it more efficient. For example, here, for A and G standard, we are using 52 subcarriers, but for N standard, we start using 56 subcarriers. We have few more subcarriers. When we merge channels, when we use bigger channels, what happened? We can use even more subcarriers. Here is 56 subcarriers, but here we can use 57 subcarriers and merge them together. So we can have better performance. We can have better efficiency. And when they switch to 80 megahertz, instead of 114 subcarriers in 40 megahertz channel, we can use 121 subcarriers in 80 megahertz channel. Okay? In each 40 megahertz, we can use 121. So we can use more frequency and more subcarriers, so we can improve the efficiency. We have a bigger channel, bigger container, and we have more boxes inside the container. What we have is better efficiency, so we can have a higher throughput. Okay? Inside that container, we are going to use something called modulation. It's not hard as it looks. It's easier. How it works, I'm going to start modulating some signals for you. The purpose of modulation is sending 0 and 1. I want to say 0 and 1. But 0 and 1, as you know, is digital. So we are using the analog signals to send you 0 and 1. Just going to make it very simple example. I want to use my voice as a frequency modulation to transmit 0 and 1. We can agree to put 0 on this voice, okay, and put 1 on that voice, okay. I'm start transmitting 0 and 1. It's very simple. You can change it to 0 and 1, and I did the modulation, and you did the demodulating. Okay? You did the demodulation, and you can write down 0, 0, 1. That's how it works, and that's this much simple. In today's words, technology, the engineers using different type of methods for this sort of modulation. They use frequencies, they use phase, they use amplitude. They merging them together to giving you a higher throughput. Okay? Let's make example for amplitude modulation. I'm going to transmitting 0 and 1 again. But what I'm going to do is change the agreement to this one. If I say with a minimum volume, it means 0, and with a higher volume, the same frequency, it means 1. I'm transmitting, I'm modulating and transmitting. I'd say 0, 0, 1, but I'm only use the amplitude. I'm using my voice volume to transmitting signal. Today, they mix the phase and the amplitude together to giving us the QAM modulation. It's very useful because we can have 16 QAM up to 1024, 1024 QAM, or even higher. So it giving us more throughput. That's 16 QAM. That's what you're familiar, 64 QAM, and what we are using at AC standard, 256 QAM. If we use 16 QAM, we can transmit 4 bits in one transmission. But if we use 256 QAM, in one transmission I can transfer a byte. So I can double my speed. If instead of 16 QAM, I can use 256 QAM. Okay? That's the modulation. Let's go to the next part. When you are watching satellite TV, if some error happen inside the transmission, you cannot ask the provider company to retransmit the signal to you because you are the only user on the broadcast channel that don't have some problem to receiving that part of the movie. Okay? For make it usable, what they did, they sending you backup. Instead of 1, 0, or 1, some of them sending you 1 backup for each beat. So you have a parity beat to make sure that you're receiving a good quality. Okay? It decreases your speed, but it gives you reliability. How it works, let's make a very simple question here for forward error correction. Instead of 1 0, here we transmit 3 zeros. The system look at the zeros. If it receive 1 error, for example 0 0 and 1 error, it changed the 0 to 1, the system can understand 0 because there is more zeros. So we are transmitting backup, so if any error happened during the transmission, you can fix it on the move. So that's forward error correction. With higher forward error correction, we can use higher speeds. So that's why in the latest technology, they use 5/6. It means 5 data and 1 parity. 5 plus 1, it goes to 6. I messed up. Okay. And 1 parity, so instead of 1/2, we are using 5/6, so we can have a higher data rate. Okay, what's next? They improved all they can do in AC standard, and the 433.3 come up from that calculation. They improve the efficiency of the carrier by using more subcarriers and make it work better. They extend the channel to 80 megahertz. They use 256 QAM instead of 64 QAM. And they use 5/6 FEC. The result was 433.3 megabits per second. Okay? What we can do next? What we can do more? We use MIMO or MIMO, depends on who asks, to double the speed. So it's so familiar when you go to a 3D movie, when you're watching a 3D movie, the cinema needs to transmit 2 images. 1 image for your left eye and 1 image for your right eye. We are doing the same by using different polarities inside our antennas in a MIMO technology, especially in outdoor applications, to transmit 2 different images, 2 different data into 1 receiver or multiple receivers by using different chains. So it can make W speed. Instead of 433.3, you can make it double, and you can have 866. In indoor applications, what's happened to you? We don't have always a direct signal, especially in 5 gigahertz applications. The signals is always bouncing around. And the time of flight of a signal is going straight ahead is not equal to a signal that bouncing to the wall and received by the user or client you have. So in this case, we can use something we call diversity, special multiplexing, to double the speed. One signal is coming from this way, transmit half of the data, and one signal is coming from here, transmitting the other half. So that's why the 3x3 MIMO works indoor, and the very close, very not so far outdoor radio applications, but we are moving to point long-range applications. The 3x3 MIMO is not working anymore. That's because of this special multiplexing, okay? For indoor applications, the both antennas is in the same direction, and it works not so bad, but for outdoor application, you need a very good cross-polarization between 2 chains to giving you a high throughput. So, that's the first generation that we already know and we already work with. What is the next generation? We are waiting for the Wave 2 AC standard, and we hope that MikroTik release it soon as the others, or even sooner. That's the MU MIMO. What is it? Before understanding the MU MIMO, we are going to learn about beamforming. What is the beamforming? If we use an omni antenna for here, for example, everyone in this conference room will have the same signal because it's an omni antenna and it spreads signal all the way equally. But if we use 2 antennas at the same time, just if you play that game in the swimming pool, you can see that. If you put your finger into the water, you'll have a wave. If you put 2 fingers at the water at the same time, the waves splash to each other, clash to each other. And what they make is some constructive combination, just like 2 waves just crash to each other and amplify each other. And some waves make it deconstructive waves. And what does it look like? If they clash to each other in a constructive wave, that both waves can amplify each other and you will have a more powerful signal. If they have a lambda 2, 100 degrees, different phase, they eat each other. We have 2 waves, one just like that and one just like that, and when we add them together, they eat each other and you will have 0 signal. We call that deconstructive. The engineers use that fact to make different patterns, okay? By using the constructive, we can make a direction, we can redirect the wave to that way that we have audience, and just don't send any signal to here because we don't have any audience and we don't want to make interference for the next room. If we can do that by computer, by chip, we can make different patterns like that. If we use two antennas, we will have these patterns. We can use it for provide internet to here, and at the next time we can use another beam to send internet to that room. If we use three antennas, we can use that technology to make more patterns. And we can have more clients. One client direct the head and one client in one way. It's not new. They already use that. But what is new here? Inside MIMO, they made some modifications. I want to make it dynamic. I want to make it automatically change the pattern. One transmission here, one transmission there. Okay? How I can understand where is my client? Okay? I cannot see the classroom. I cannot see the conference room. How I can understand I have a client here and I have a client there. When I want to transmit some signal here, I can use this beam. When I want to transmit a signal there, I can use another beam like that. We have two modes. One of them is implicit mode. I can listen. I can hear my client voice from that part. So when I want to transmit a signal, I can transmit the signal to there. And another feedback, another signal from there, so I can repeat that signal to there. So that's how the implicit mode. But there is a problem here. Sometimes when the client from this side is sending me a signal, it bouncing there and I will receive the signal from my back. But when I'm sending the signal to there, it's not bouncing very well, so I make a mistake to finding my client. They improved that by explicit mode, so when I'm sending a signal, I'm waiting for my client feedback. When I'm sending a signal here, the client send me, good job, it's a good signal, okay? So, by explicit mode, it works better. But the problem is, my client, if don't support the explicit mode, I cannot use that. For the implicit mode, I don't need any special client. But for the explicit mode, I need some client can understand the feedback and send me the feedbacks. So, maybe it's not working very well. It also gives us more gain because we are using antenna arrays, so we can combine some waves and it gives us more powerful beam. So instead of simple omni 2 dBi, when we are using this mode, we can reach higher gains up to 12 dBi if we are using 4x4 MIMO. Okay? So it can even improve our gain and it can give us the higher range because we can have a higher gain antenna. What is happen in MIMO by using the beamforming at the same time using splitting channel, instead of having a hub, just like hub inside our network, we are using a switch. When we are using a hub inside our network, what's happened? We can only have one speaker at the same time, because we will have a collision. Inside the wireless network today, we can only transmit or receive signal. If some of our users start watching a movie, the other clients having the lower speed, and they should wait for the packet going to that client. But in MIMO, what is happening? The access point can split the channel, also the beams, and at the same time, I can transmit a video here, and I can transmit data here, and I can transmit voice over IP there. So by using that technology, instead of one access point, it looked like I'm using 4 access points, okay, at the same time. It's really nice. We are waiting for the new products is coming. That's how it works. It split the channel and also use different beams for each user. One beam for here and one beam for here. So we can even reuse the frequency. It's a good idea. How it beam forming, how it make beam forming. It use something called a steering matrix. When I transmit a signal at the same time from these 2 antennas, what's happening? I'm sending a signal to that direction. But if first I'm transmit a signal, and with a short delay, I'm send another signal from here, I can have this steering matrix. First of all, I'm transmit a signal from here, and with a nanosecond difference, I'm start a signal from here. Instead of sending a signal into the front, I can sending a signal to the left. Because first I start making a wave here, and I start making a wave after that here. They shift the beam to this side. So inside the MIMO, the system will use the steering matrix for learn the clients and send the signal to another direction. By using that, we can use 4 clients or 3 clients at the same time, 2 channels for 1 client, 1 channel for 1 channel for 1. So it makes us happy. Okay. Is there any more improvements possible here? It is not, because if we, for example, change the 256 QAM to 1024 QAM, we can have 24% more speed. But the problem is the chance of error will rise to 400%. So it's not good at all. We don't want it. What will be next? The next technology is coming up is 8.2 AD, 11 AD. They changed the frequency at all, and we shift to 58 gigahertz channel, so we can have a very big channel, 2.16 gigahertz channel. It's looked like this. For AC, we have 80 megahertz and 160 megahertz. But here, we have 2.16 gigahertz. It's so big. So, we can have very good throughputs here. For example, with a very simple configuration, we can have 6,756.75 megabit per second. It's more than we need, believe me. And if they use MIMO in the future, it can goes up to 13.6 gigabit per second. So it's more than enough. So it's enough for us, let's say. What about the interference? And for long-range application, there is something very special for this frequency. It is have the same resonance with the air. So if we have a loss for other frequencies like this, we have a very big rise up here for 458 gigahertz. So the air will eat our signal, so we will have very less interference, but short range communications. Because the air don't let us, our signal travel so far. The resonance of the air will eat our signal and change it to temperature, higher temperature. So just like what the microwave ovens do with 2.4 gigahertz by water, it's happened to 58 gigahertz for air. So we cannot have a very long-range communication with 58 gigahertz. But the good news, we will have less interference. So let's see what is happening in 50 years. I'm just going to tell you the future. Einstein find something very weird in quantum mechanics. They found something called spooky action at the distance. What is that? If you have entangled particle, it can be photons, it can be electrons. If I keep one particle here and one particle in somewhere else, if I rotate this particle, the other particle with the same time, with no delay, will rotate to 100 degrees another direction. It's too weird. Even Einstein don't understand how it's happened, and we don't have any explanation today, but it's happened. Every particle have something called quantum state, and if we can measure the quantum state of the particles, and if they entangled, if we rotate one of them, the other particle will rotate at the same time, exactly same time. There's no matter how they far, but they can rotate. Is it tested? Yes. It's tested in China with 2 fiber optic lines. They make the entangled photons with a laser machine. They send one particle in one direction and one particle in another direction, and they use some random filters, and they start to count the number of the particles that they really match together. The result is 100% of the particles is matched. And the speed of that system is amazing. 10,000 times faster than light. Or even more faster. What we can say, for now, we test 10,000 times faster, and these action is take place in the no time. It's very fast. So what we will have in 50 years, we will have the new MikroTik routing the planets, and that much gigabit per second with 0 millisecond delay between Earth and Mars. So, thanks for your time. Time for questions, if there is any questions. No. Okay.